Hi, this is NV Fitton to talk with you about completing the square. That always sounded very ooky to me, and the truth is I wasn't sure I could understand something that sounded so peculiar. But once I learned what it was, I like it a lot because I find it more versatile than using the quadratic formula, and I make many fewer errors by completing the square than I ever did with the quadratic formula. So, off we go. Oh, uh, right now we are talking basics. This is part one. Okay, so basics. Let's take a quadratic function, y equals x squared minus 6x plus 9. Now, a perfect square might be a number, let's say b squared is 49. Then we know by the definition of square root that b is 7. And we're going to do something similar with this. We factor it into x minus 3 in this case, that quantity squared. And so that means that this expression, x squared minus 6x plus 9, is also a perfect square. Well, the beauty of factoring this, there are two things. One, this is a standard form where we have y is equal to x squared, either plus or minus 2ax plus a squared. And we have known for a long time that that factors into x plus or minus a squared, right? Okay. And in addition to that, so that's one thing, we can factor it easily. Two, we can easily graph it with what we know about transformations. If I look at this form, well, I can't say that I know by looking at that equation what the graph of it looks like. But if I look at this form of the equation, I say, why, of course, that is a garden variety parabola shifted 3 units to the right of the origin. Okay, so I like perfect squares. Let's look at another one. Oh, wait a minute. I wanted to say one more thing about this. If I think of 2a as equal to 3, then I know that 3 squared is equal to 9. And I'm going to be keeping that in mind as I move along. Okay, that idea. Now, back to our next example. Y is equal to x squared plus 2x plus 1. Well, somewhere in my mind I think, okay, 2a is equal to 2, so a is equal to 1, and a squared is equal to 1, so aha, I have a perfect square. And the equation of that perfect square is, I can factor what we see up above into x plus 1 squared. And I can easily graph that using transformations. Okay, so much for perfect squares. Now let's look at something that is not a perfect square. Y is equal to x squared plus 2x plus 5. Well, comparing it to what I had up above, I see that it is not a perfect square, but it's not far from this expression that is a perfect square. If I break that 5 into 1 plus 4. Now, how come I choose 1 plus 4? Because 2a is equal to 2x. Oops, just 2. So that means that a is equal to 1 and a squared is also equal to 1. So here's my 2a and here's my a squared. Okay, and looking again at the equation, now I'm going to rewrite it as x plus 1 squared plus 4. Okay, so what? Well, I don't know how to graph this, but I do know how to graph this using transformations. So I just need to, let's see, move it 1 unit to the left and 4 units up, and there's my graph. Okay. Now you may remember some stuff about negative 2b over a and h and k and I don't know what from your previous experience graphing parabolas. For me, man, this is easier. Okay, let's look at another example similar to this. How about this? Y is equal to x squared minus 6x plus 12. Now, I think to myself, if 6 is 2a, then a is equal to 3, and a squared is equal to 9, and I know that 12 is equal to 9 plus 3. So I'm going to write this x squared minus 6x plus 9 plus 3. This has the benefit that on the left I have stuff that is a perfect square. So I can write this as x minus 3 squared plus 3. And this I can graph easily too. Now, why this is called completing the square, I do not know. But I know how to do it, and I can do it very quickly, and I can do it a lot better than I can do the quadratic formula. So I'm sticking with it. This is the end of our